In this video, we're going to learn how to use differentiation to find stationary points on a graph. Let's get into it. Stationary points are a key feature of polynomials and some circular functions. There's actually three different types of stationary points, and they are local maxima, local minima, and inflection points. All stationary points share the same feature. They all have a gradient of 0. A local maxima can be thought of as a peak on the graph. This isn't to be confused with the true maximum of that function though. For example, this function here has a local maxima at negative 2, 16, but its true maximum would be positive infinity since the function rises forever. A local maxima can be identified by observing the gradient before and after the point. To the left of the point, we should expect a positive gradient since the graph should be rising to meet that stationary point. And to the right of that point, we should expect a negative gradient since the graph should be falling away from that point. A local minima can be thought of as a trough on the graph. For example, this graph has a local minima at 2, negative 16, but that's not the true minimum of this function either. The true minimum would be negative infinity since the graph descends forever. We can identify a local minima in a very similar way by observing the gradient either side of the point. The gradient to the left should be negative since it's falling, and the gradient to the right should be positive since it's rising. And lastly, we can talk about inflection points, which on this graph appears at 2, 2. Just like the previous two stationary points, we can also observe an inflection point by observing the gradient either side of that point. But unlike the other 2 points, there's actually going to be 2 possibilities for inflection points. Firstly, we have an inflection point if the gradient to the left is positive and the gradient to the right is also positive, just like in this example. And lastly, we could also have an inflection point if the gradient to the left and right is negative. As long as the gradient doesn't flip either side of the stationary point, then you have an inflection point. Just to be clear, every stationary point has a gradient of 0. All we're doing here is observing the gradient before and after the stationary point. Okay, now that we know how to observe stationary points, it's time to figure out how we can use a derivative to find them. Remember, the key feature of any stationary point is that it has a gradient of 0. And we also know that the derivative of a function is a function that tells us the gradient of the original function for any value of x. So if we're only interested in points of 0 gradient, then what we do is set the derivative function to be equal to 0 and then solve for x. This will give us the x coordinates for all points of 0 gradient. For this cubic, we find that the derivative is going to be 3x squared minus 12. We then set that derivative to 0 and then solve for x. Now in this case, this requires a bit of factorization and a null factor law approach. What this has done is tell us the x coordinate for all stationary points on the graph. All we have to do from here is sub in those x coordinates back into the original function to get the corresponding y coordinates. And sure enough, we get the original coordinates that we had in the previous example. Okay, so now we know how to find stationary points, but that only tells us where they occur, not what type of point they are. And we can't always rely on being able to observe a graph to figure that out. There is another way. We can determine the type of stationary point that we have by using the second derivative test. Let's see how that works. First, you find the second derivative of the function. Now, all this means is that you're going to find the derivative of the derivative function, f dash dash x. And in this case, that's going to come out to be 6x. What we're going to do now is sub in the x coordinates that we found earlier into that second derivative, and then observe the sign of the result, positive or negative. If the result is negative, then what you have is a local maxima. And if the result is positive, then what you actually have is a local minima. And lastly, if the result is 0, then you have a point of inflection. And sure enough, we observe that x equals negative 2 is a local maxima, and x equals 2 is a local minima. This is how you sketch higher order polynomials when their turning points don't occur on the x-axis. Stationary points are tested all the time in the exam, and they're usually tested in an application style question. The classic example is to find the maximum volume of a box. Now, in an application style question, there's usually several parts before that question that lead up to it, so let's start with those. The first task is to show that the volume is equal to the polynomial that's listed in part A. To find the volume of any box, we need to know the length, the width, and the height. The height of the box is always going to be given by the width of the squares that were cut out from the original sheet. And in this case, that variable is going to be x. Now for the width. The width of the entire sheet is h. This is not to be confused with the height. Apparently the examiners just wanted to make life hard here. So the width of the sheet is h, but to form a box, we have to cut out squares from either side. So what you do is you take h, the entire width, and you subtract x from either side. That is the same as subtracting 2x from h. So our width is going to be h minus 2x. We do a similar thing with the length. We started with 2h, but we had to subtract 2x's away from it to form the box. So our length is going to be 2h minus 2x. And now that we have all the required terms, we just substitute into the volume equation. And lastly, we're told that h equals 25. So we're just going to replace every instance of h with 25 and then do a bit of factorising to get it to look exactly like the polynomial in part A. The next question asks us to state the domain of the volume equation. Since the volume equation is written entirely in terms of x, then we need to start thinking about possible restrictions on x. This is where the specific application actually really comes important. For example, the question tells us that the volume needs to be greater than 0. And this can only happen if x, the height, is greater than 0. Otherwise, it would be a perfectly flat sheet of paper. It's also worth thinking about the potential upper bound of x. For example, we know that x is the width that we cut out from either side of the sheet of paper. There's a limit to that. We can't just cut out 1,000 meters from x on either side because the sheet is only h or 2h long. So what you do is you take the shorter side and you divide it by 2. That's the maximum possible value that x could be if you were to take x from either side of that sheet of paper. And since we know that h equals 25, then half of 25 is going to be 12.5. So our upper bound of x is also going to be 12.5. And then from there, you just write the domain as an interval. Next, we're told to find the derivative of the volume equation. This is tech active, so just plug this into the CAS and it'll tell you the derivative. Otherwise, if you wanted to do it by hand, what you would have to do is expand out the brackets and then use the power law to find the derivative of the resulting polynomial. And finally, after all of that, we're told to figure out what the maximum volume is. Now, if you plot the volume equation over its domain, what you see is that the maximum volume occurs at a turning point. And since a turning point is a stationary point, it has a gradient of 0. So if you want to find the coordinates of that point, you find the derivative and you set the derivative to equal 0. We already have the derivative, so all we got to do is set it to equal 0 and then solve for x. This will actually give you 2 x solutions, but only one of them is going to fit within our domain, so you can just ignore the other one. And now that we know the x coordinate of the maximum volume, we then sub that back into the volume equation, not the derivative equation, but the volume equation, and then solve for the corresponding y coordinate, which would thus give us the maximum volume, since volume is on the y-axis. What this question did was outline the key steps that you need to take to find the maximum or minimum of most application-style questions. You start by plotting the function over its limited domain, and what you find is that most of the time, the maximum or minimum is going to be a turning point. From there, since it's a stationary point, you just find the derivative and then set it to 0 and solve for x. That x coordinate will then be plugged back into the original equation to get the corresponding y value, which will then be the maximum or minimum value that you're after. There is one slight improvement you can make on this process, and that is instead of finding the derivative and then setting it to 0 and solving for x, you can use the functions fmax or fmin in the CAS. These functions do that step for you. And even better than that, they only give you one answer. You don't have to pick between 2 possible x values. It'll just give you the one that is in your specified domain. On that point, just be sure that you set the domain properly. If you don't include a domain, then the function will assume it's the maximal domain, and it'll just give you x equals infinity or negative infinity. Either approach works. Usually you'll have to find the derivative anyway, but at least this can save you a bit of time if you don't need to do that. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll send you to my website.